Okay, so we are going to discuss just about the requirements for the second assignment. Alright, so I'd like to just clarify the concepts. So generally I'll just expand what was discussed or what was presented in section 3 of the assignment specifications, so that at least you have a better understanding on how to move forward with the assignment. Okay, so as you know, the purpose of this assignment is to actually simulate a distributed wireless sensor node. Alright, so the assignment, well, we did fix the number of nodes. I would have actually preferred to make the nodes a bit more dynamic, but nevertheless it's ready in the specifications, so let's keep it there. Alright, so here what the assignment says is that you have 20 nodes and a base station. Alright, so what I'm doing here is that I'm just representing the nodes as a grid, as similarly what is shown in the specification also. Alright, and what it says here is you have a base station over here. Okay, so the rules as mentioned in the assignment is that what it says that each node, each sensor node can communicate with the base station. So it doesn't matter, I mean in the assignment they put the example satellite communication or something like that. Okay, so each sensor node can communicate with the base station, but each sensor node can only communicate with the adjacent nodes. Okay, with the adjacent nodes. So in this particular context, for example, like node 0. So for node 0, who is node 0's adjacent node? 4 and 1. For node 6, the adjacent nodes are 2, 5, 7 and 10, and so forth. Okay, so based on this setup, you are asked to write a program to actually simulate conditions to which an event is triggered, and then how the event is actually relayed back to the base station for logging purposes. That's the general idea of the assignment. I mean, to keep it as straightforward as possible. Now, but when you start going into the details, then things can be a bit more tricky. All right. So the first rule, it says what? The event detection criterion. In order for an event to be recorded by a wireless sensor network, at least 3 adjacent nodes to a reference node must simultaneously report their activations to the base station. Now that one particular statement is a bit can be interpreted differently. Alright, so now what it says is this. Okay, so in order for an event to be recorded by the WSN, wireless sensor network, which means for an event to be triggered, alright, three adjacent nodes to reference nodes must report their activations. So for example, let's look at let me use a black pen. Let's look at node 6. Okay, let's look at node 6. So who are node 6's adjacent nodes? It's 2, 7, 10 and 5. Alright, so 3 of these adjacent nodes must report before I go to the simultaneous, must report a common activation value. So node 6 will get 3 different values from the adjacent nodes. So here you got 4 nodes. So any 3 values from these adjacent nodes, if they are the same, that constitutes an event being triggered. Okay. Now the question is then, who reports it to the base station? Now, so if you look at the statement here, 3 adjacent nodes to reference nodes must simultaneously report their activations to the base station. So so some students might get the idea that, well, if for node 6, let's say for example, if nodes 2, 5 and 10 were to report a same value to node 6 triggering an event, nodes 2, 5 and 6 should then inform the base station about the event. Not wrong, it's correct. Some students may interpret it as, because node 6 is the one that's comparing the values, alright, so node 6 determines that nodes 2, 5 and 10 generated the same value triggering the event, so node 6 is the one that should report the event to the base station. So either way is fine. Okay, but if you ask me, I think you know which method is a bit more easier to implement, so I won't go into the detail. Alright, okay, so that is the idea. Okay, and then what information you actually send to the base station is that's the one that determines your score for the assignment also. All right. So now let's say I go with the second approach, whereby three or more adjacent nodes to a reference node triggers a common value, constituting an event activation. But the reference node is the one that sends the message. The reference node is the one that sends the message to the base station. Okay, so how do you go about implementing that? Okay, so that's the idea now. So the first thing is this. How do you determine who are your adjacent nodes? How do you tell? So, like here, in this example, I have 12 nodes. And the assignment is 20 here, so I made it 12 because it's easier to draw. Okay, just for illustration purposes. So in this case, I'm running MPI run -NP13. So 12 nodes, the 13th one is the base station in this particular example. Now bear in mind that you're not creating 2 MPI programs here. You are creating 1 MPI program. Okay, the 1 MPI program, in the program you will have logic that will determine who will be the base and then who will be the sensor nodes. Okay, so remember you're only writing 1 MPI program, but the 1 MPI program will be executed n number of times. In this case, 21 times, because 20 for the base station, 1 for 20 for the sensor nodes and 1 for the base station. In this example, I put 13 here. Okay, so now coming back to the visualization. So because we are representing this as because we're representing this as a 2 grid, and then we have nodes with adjacent nodes. So maybe let's put a 2D coordinate. For example, like here. So for node 0, the 2D position is what? 0, 0. This is 0, 1, 0, 2, and then 0, 3. This one is what? 1, 0, 1, 1, 1, 2, 1, 3. This one is what? 2, 0, 2, 1, 2, 2, and 2, 3. Am I correct or not? Yes, sir. Alright, looks pretty 0, 0, 1, 0, 2, 1, 0, 1, 1, 2, 1, 3. Okay, looks pretty good. Okay, so why not we just represent it as 1 dimension vector? Why do I put this as a grid? Because it's easier to visualize. Alright, if you put it as a 1 dimension vector, it's quite hard to see who are the adjacent nodes for a particular reference node. Alright, I mean you can mathematically do that, but just for the purpose of illustration, I'm just making it a 2-dimensional grid. Alright, so once you have a 2D grid here, okay, so now you know each node who are the adjacent nodes. Now, let me ask you this question. Let me throw you this question. Based on this grid, which nodes will never have an event triggered? The corner nodes, exactly. The corner nodes will never have it. So this in this case will be node 0, node 3, node 11, and node 8. Because why? For node 0, the adjacent nodes are only 4 and 1. Or in this case, 0, 1, and 1, 0 in 2-dimensional grid. Now, having said that, that doesn't mean in your code you have to go and detect who are the corner nodes and then you don't do anything with these corner nodes. No, no, no. Each node, each sensor node is responsible to send a signal to the adjacent nodes. At the same time, each node also receives a signal from the adjacent nodes. This is very important in logic. So you don't care whether or not which nodes can report to the base station or which nodes will never report to the base station. Don't do that. That will just complicate your entire code. Alright, you just keep it to the point. So which means that in your program, alright, when in your program structure, each node starts by first doing what? Each node starts by first doing what? You can put like this. Okay, it generates. This is just a sample, okay, just a sample. Okay, there are several ways of implementing this architecture. Okay, this is a sample here. So one is we generate a random number. Okay, a random number. So generating a random number is covered in last week's lab already. So by now you should be familiar with all of this already. Alright. Now, preferably, I think you should generate random numbers which are quite small. Otherwise, the odds of having three adjacent nodes to reference nodes coming out the same number is very slim. Alright, you want to run this experiment or this simulation by having more events triggered. If you put very large random numbers, the odds of having three adjacent nodes to a reference node generating the same numbers are very slim. So generate a random number wisely. Okay, all right. So once you generated a random number, so this I'm doing this for each node. So each node does this. Each node does the following. You generate the number. Then after that, what do? You send the random numbers. You send the random number to adjacent nodes. You send the number to adjacent nodes. Now, this is the tricky part. So, how does each node know who is their adjacent node? Now, let me warn you all. Don't be so cheeky. And then in the code there put if I'm node 0, my adjacent nodes are 4 and 1. You do that. Then else if my node 2, I'll do, your code becomes so fixed for 20 nodes. I mean, even though if it works, when I look the code, I find a kind of structure, I'm going to minus marks already. Okay, you should do proper logic. Alright, you should do proper logic control for how you structure your code. Okay, now, so how can you tell each node? For example, node 6. How can node 6 tell that 5, 7, 10, and 2 are their adjacent nodes? Yeah, any ideas?
MPI card shift.
Yes. So one way is you can use Cartesian, MPI Cartesian. So you can do MPI card create, card shift to then determine who are your adjacent nodes. We have done this before, I think in week 4 or week 5 of the lab. You can check it out and see. All right. So by all means, use that to actually determine who are your neighborhood nodes for each node. Okay. But at the same time, there are other ways also to determine who are your neighborhood nodes. Purely based on what? Purely based on your rank, size minus 1, and also in this case, your column, the grid column width. The grid column width. So of course, each node knows their rank, the global rank. It knows the global rank. Each node also knows the number of processes running. But this time I put here size minus 1. Okay, or maybe I should put here say for example P minus 1. P is the number of running processes. Okay, why I put P minus 1? Because we are isolating out the base station. Alright? And each node also knows the grid column width. Let's say if in this case you have a 3x4 grid. You can have a 3x4 grid, you can have a 4x3 grid, or you can have a 2x6 grid, or you can have a 6x2 grid. These are the possible grids for a 12 node configuration. So for 20 you can figure out what kind of grids you want to, what kind of grid setup you want to do. Whether it's going to be 5x4, 4x5. Yeah, but then they say 4x5 here. Then I'm sorry. You can follow 4x5. Alright? Okay. So, by this example, I use 3x4. Okay? So based on that, okay, let's say, okay, so how do you write a code? How do you write a code that would translate rank 6 one-dimensional index into a two-dimensional index? What's the idea? How do you get what is the row position for rank 6? What is the column position for rank 6? What's the formula? What's the formula? Who can tell me? Okay. Anyone? What is it? So you take what? You take the rank value, divide by the grid column width. The grid column width. So in this case, what is it? It is what? It is 6, rank 6 divided by 4. You get an integer value, 1. And then, what is the column position? 6 divided by 4 for its remainder, which is what? 2. So, for rank 6, the two-dimensional index is 1, 2. Over here, you can see. So, it works for others. For example, like say 11. 11 divided by 4 is what? 2. 11 divided by 4 for remainder is what? 3. So, it's 2, 3. So, basically, once you compute your two-dimensional position of your rank with respect to your grid size, then after that you can then use this two-dimensional position to then determine who are your neighborhood nodes. It's logic already after that. You can then do plus 1 column, minus 1, plus 1 row, plus 1 row, minus 1 row. But of course you need to check for boundaries. If you exceed the column width, which means you already reached the edge of the column, and vice versa. So once you determine that, then after that you can now send the random numbers to all of the adjacent nodes. Okay, so you can send the random numbers, so you send them. So now let me ask you a question. Okay, let me explain to you first, then ask you a question. Okay, so now you send the random value to all adjacent nodes. I already put it here already. Let me come up to here. Okay. After you send this, then what do you do next? Then you need to receive the random values from adjacent nodes. So first you send to the adjacent nodes. So for example, like 6 here was sent to 7, 5, 2 and 10. After that, 6 will then expect to receive from 7, 5, 2 and 10. Can you follow or not? Now let me ask you all this question. Please answer me. In this case, which send should I use? Blocking send or non-blocking send? Would blocking send work or not? Imagine each node needs to send the number that it generates to the adjacent nodes. And at the same time, each node needs to get the random number generated by the adjacent nodes. So my question to you is, do you use blocking send or non-blocking send here? So I can't, someone be louder a bit. So, I know they're talking so loud here. Okay, so what do I use here? Would blocking send work or not? You sure it'll work or not? Okay, by right, a non-blocking send would be more reliable approach. So you can use I send and I receive, and then after that you call MPI wait all. You call I send, I receive, and you call MPI wait all. So that ensures that all the nodes, all the adjacent nodes receive the value you send, and then you also receive all of the values from the adjacent nodes. Okay. Now once you've gotten the value, so now for example, like each node will have the receive random values from the adjacent nodes. Okay. So now, for example, like here, for example, for node 6, this is for node 6. Node 6. Who are the adjacent nodes? The adjacent nodes are what? 5. Maybe I should put it 2, 5. What's the other one? 7 and 10. So let's say for node 6 receives the following values: 100, 100, 150, 200. So it compares the values here. How many values occurred? How many of the same values occurred more than 3 times, or 3 or more times? None, isn't it? So continue back the iteration again. Continue back the iteration again. Can you follow or not? Now let's say next cycle, node 6 now receives 100, 100. Okay, let's say this is for iteration I equals to 10. Now at iteration I equals to 11, let's say at the following iteration, because we are running this in a loop, so we can run this as many iterations as you specify. Alright? Okay, so now let's say I equals to 11. Let's say I equals to 11. Okay, so now let's say I receive now 100, 100, or maybe I just put here, I put 100, 100, 100 and 200. Just an example here, example only. Okay, now in this case, we know that we have three values received from the adjacent nodes which are similar. So that constitutes a triggered event. So once this condition is met, then this node 6 will send a message or messages to the base station to notify the base station an event has been triggered. That's the idea. Now, so based on some of the forum posts and so forth, so one interesting argument is this. So can I compare the values received at an iteration with the previous iterations or not? Now, you didn't mention in the assignment. So that's where we encourage you. I mean, if you look at it at per iteration, it's quite easy. Okay? But if you look back at previous iterations, then it becomes a window-based approach. A window-based approach. You have a window. So normally you call this tuple-based. I won't call it time-based because you're running an iteration. Okay, so maybe you have a window of tuples. So which means that at one, so let's say you have a window here. This is a window. This is a window. So let's say the window is separated based on iteration. So let's say the window size. Let's say a window size is 3. Let's say the window size is 3. So at every cell of the window, you store all of the received values from an adjacent node for one particular node. This is for one node, one node. So in this case, when let's say I equals to 9, I equals to 10, I equals to 11. So I equals to 10, you had what? You had 100, you had 100, you had 150, and then you had 200. And then here, you have 100, 100, 100, 200. So, if you use a window, then you can move the window. It's like a moving window. So then you can compare the values within the window. And if you have 3 or more similar values within this entire window, that considers the event also. But implementing that is harder. Implementing that is harder. I mean, we would appreciate that kind of technical work if you do. If those of you all are aiming for a very good grade. Okay? So of course, safer one is just look at it per iteration. If you want to do it as a moving window, so every time we move the window, so now at the next iteration, this becomes I11, I11, I12, and then I10. So which means that in this case, I10, I11. At the next iteration, the window moves, the window slides. So now you got I equals to 12, and then you have a new values coming in inside here. So it's like a moving window, a sliding window. You can do that. But the assignment didn't explicitly ask you to do that. It's something that we do welcome this kind of thought. Okay, so it's up to you whether you want to do it, or if you just want to look at it per iteration, that's fine. So that's what a node does. The node reports to the base station, and this continues in a while loop continuously. Now the question is, how long do you execute this while loop? So this is tricky because this is like an experiment. It's like a simulation. So you can put a while. Let's say while x is less than 1000. X is a counter, then every time you decrement the counter until while x is still, maybe this is a bad one. Okay, sorry. Maybe I should put while x is larger than 0. Okay, while x is larger than 0, maybe you set x to 1000, then you decrement it until x becomes 0. So you can run it for 1000 times. Okay, but I would prefer if you put a sleep at the end of every iteration before you repeat the for loop again, because you don't want, because you're not really measuring performance. It's not a data parallelism problem like the first assignment. This is more to actually investigate inter-process communication. Although there are some elements of data parallelism in your encryption. I'll come to later on a bit. Alright? So the idea is that you can run this at every iteration, but I prefer you put a sleep if possible to reduce the strain on the nodes, on the system. Okay, I mean not saying you don't put a sleep it would crash or what, no. It's just that to make it run, to reduce the strain, if any also. Okay? So now, this is a node. Any questions on the node or not? Answer node, okay? Quite clear, isn't it? I mean, if you look at it, it's quite easy. So whether or not you want to use 1D to 2D and then 2D back to 1D for sending is up to you. So to convert back from, if, for example, like if I want to know, now I know my adjacent nodes. So how does node 6 know how to convert 1 3 back to 7? This one you know already. You've learned this before in multiplication. Very simple. How do you do that? How do I get the adjacent node here? For example, like how do I convert 1 3 into a 1D value? What do I get here? I take what? I take the row position multiply by the column width plus the column position. So what do I get here? 1 times 4 plus 3. So 7. So for 1 3 is 7. So you can either choose to do this method or you can use Cartesian. So it's either way. It's fine. It's up to you. Don't do both and then report both and then say which is better. No, this is not assignment 1. That's why you just choose one method which you think is suitable for you to implement and things like that. Okay? Now the base station needs to continuously poll for messages. So how you do that? How does the base station? The base station only receives messages from a node which decided that an event has been triggered. So how does it do that? Come, I don't want to waste time already. I'm running so long already with you. Yeah. So how? What do I do? Come on, John. I'm going to be in limelight. Okay. Anyone? Haris? How? So the base station will just continuously call MPI receive. But does the base station know which node to receive from or not? No, isn't it? So what do you put in MPI receive? Any source, exactly. You receive from any source. That's all. MPI receive any source. And then when you receive the message, then you log it. Now the logging is the one that determines how technically deep you have gone into the assignment. So the logging can contain information. What kind of information? I already put in the rubrics already. I mean some sample. I mean I hope you can do better than the rubrics also. Okay? So you can contain information about what? First of all, timestamp. You need to know at what time the events were generated that triggered what time the values were generated that triggered the event. So this has to be a proper timestamp. Don't give me just one integer number and say, oh, this is a timestamp. I won't accept that. You must give a proper timestamp, date, time, and seconds, all the way to seconds. Okay? So that information is sent by the node to the server. Not server, base station. Base station. Alright? Then on top of that, you can send information about the nodes, like what is the values, what were the values generated. You can also send information at the point of the event detected, when was the last time the event was detected. So you can show how many intervals has elapsed or how much time has elapsed since the last node, the last time this particular reference node generated the event. So there's a lot of information. You can also include what is the time. What is the time required to communicate with all the adjacent nodes? So you can measure the time to do MPI I send and I receive. You can measure all the time. You can put a MPI W time before you call I send and I receive, and then you can see. You put W time, MPI W time before MPI I send, and then you put the MPI W time again after MPI wait all. So you can measure you can measure the communication delays, if any, between the nodes. So all of the information can be sent back to the base station to be logged. Now, also on top of that, you can also send back the IP addresses and the MAC addresses of each node. Now, you may argue with me, this doesn't make sense. I'm running my program on one laptop or one computer, only got one IP address. I mean, why do I want to send each node with different IP address? I put that there in the rubrics because I was hoping to give Monarch a try. Try a Monarch, but you need to configure Monarch such a way that each node, or at least a group of nodes, run on different computers, different servers within the Monarch cluster. So that one you have to go and read the Monarch user requirements and find out how to do that. Okay, that way you can get different IP addresses already, or different MAC addresses. So all of the information can be then sent to the base station, and then the base station can then record it into the log file. Now, how does the base station know when to expire? Let's say you run each node for 1,000 times. So you got 12 nodes here, each of them run for 1,000 times. Doesn't matter how many times you generate the event, doesn't matter, it's a random one. And then after that, they exit the for loop, and then they all got MPI finalize, happy ending for the nodes. How about the base station? How does the base station know? The base station needs a continuously poll for messages. So how does it know? How does the base station know that all the nodes have ended? So this one you think about it. Okay, it's actually fairly simple. I'm sure you can think about it. Okay, and then when the assignment say what? One of the criteria is what? Less than 4 messages sent between the node to the base station for every event. Now, meaning that because you're going to send a lot of information about an event being triggered. So you want to see how many times you have called MPI send to the base station to send a particular message. So this is where you can be a bit creative, how you actually want to pack the messages into one structure or into one large character array, and then you send it out as a string. That one is up to you. You leave it to your creativity on this particular part here. Alright? And then of course, the important thing is the encryption. So each message communicated between the nodes and any messages sent to the base station, should be encrypted. Okay, so the encryption is an open-ended problem here. So you can, depends on how much effort and time you put into the assignment. So if you, let's say for example, if you want to keep it very simple, you want to do a simple XOR, exclusive OR, just to encrypt the data with a simple key, can. But even if you try putting OpenMP to try to improve performance, you will not get, the speed ups will not be significant, because XOR is a very trivial operation. Unless you try downloading standards from the internet, proper encryption standards, and some of the encryption standards implementations, they already have built-in OpenMP. So I leave it to you to search online. This part is like some research. Okay, you can find any encryption algorithm. Okay, if you get the C code and you put OpenMP inside there, that's fine. If you find any encryption algorithms which already has OpenMP implemented inside there, that's fine also, as long as you properly mention it in your report where you got the source from, which site you cite it properly, and then you can report how this encryption algorithm actually helps the performance. How OpenMP with this encryption algorithm actually helps the performance of the encryption and decryption process. All right, so generally this is the assignment in essence. Okay, another question I got from a student is saying that So you can think, I mean, I don't want to disclose too much. Given quite a lot already here. Okay, but you can also think, do I send the information for an event triggered per iteration, or do I send in batches? That probably happened. Okay, so can you follow me, guys? Do I send, so at every iteration, do I send that particular event triggered to the base station for each node, or do I collect it first and send it in batches, or send it at the end of the program? Up to you. That's where you can measure the impact of communication. Now, so in the first assignment, you measure the computational time. Maybe here in this assignment, you can start measuring communication time. Then you can determine what is the best approach to send the messages. Whether you want to send to the base station at every iteration, or you want to keep it in a batch and then send it in one go after let's say 100 iterations, or you want to send it all at the end, can. But the timestamps must be important. So, but then again, also you have to be logical a bit, because you are supposed to simulate a wireless sensor network. When you want to send the event to the base station, why would you want to wait until the end of the program? I mean, in terms of real life implementation, if imagine these are all climate sensors that can detect fires or something like that. When you detect an event for a fire, you want to send the event immediately to the base station, isn't it? I mean, example, in the real world scenario, why would you want to delay, stock up first and then report? I mean, it depends on the use case. So it's up to you, this one. Okay, any questions? It's fairly straightforward. I think many of you all, if you are very familiar, assignment 1, assignment 2 should be quite doable. Okay, any questions before we end it?
So
Yeah.
the tile is always 4.5 in this case.
Here they put here arrange 4x5, but we welcome you if you want to do 5x4. Or I mean, it's fine.
Because it impacts on the adjacent node.
That's true. It has an impact on the adjacent node. If you do it 2x10 also, it has a bigger impact on the adjacent nodes also. I didn't specifically put this requirement in assignment. I'm not going to modify the specifications now because it's too late already. I mean, if you want to put it n times m grid, that would be pretty impressive. You can work for any grid layout. That would be pretty good if you can do that. But that's optional. I mean, it depends on how far you want to push. Okay, so that's the thing. All right. Any other questions? Any other questions? Okay. All right. Thank you. Thank you.